In 1940, the head of the Census Bureau proposed to Congress a slightly different way of apportioning called the HillHuntington method. This still uses rounding, but it uses rounding in a slightly different way. So let's look at this method. Now, this method is currently being used, so it is the one that is currently used by Congress to reapportion every 10 years. So the standard methods, instead of looking at example first, I'm going to look at how the rounding works. So we always start with the standard divisor and the standard quotas found. That's the same in every method. Once you find the standard quotas, they're rounded, but instead of using normal rounding rules or standard rounding rules, we're going to use what's called a geometric mean. The geometric mean of the whole numbers on either side of the standard quota for rounding purposes. It's going to create a new border for rounding instead of 0.5. And then once we have the rounded quotas, then we're going to make the decision about using new modified divisors, again, using the same rule we had before. The new modified divisor should be lower than the previous divisor if the total is too low, or higher if the previous divisor gave you a total that was too high. And then you recalculate with a new modified divisor and start over if you don't get the right total. But let's talk about this main difference, this geometric mean. How does rounding with a geometric mean work? Well, let's first talk about what a geometric mean is. Now, the geometric mean of two consecutive numbers, a and b, would be the square root of a times b. So you actually, in this calculation, are going to multiply the two numbers together and then square root them. So if you have a standard quota, say 3.47, and we wanted to look at rounding it with geometric mean, we would first find the geometric mean of the two numbers on either side of 3.47. Now the two numbers on either side would be 3, because that would be if you cut off the decimal, and 4 if you round up. So you round down and round up, and we're going to use those two numbers to find a geometric mean. So 3 and 4, I'm going to multiply them, and then I'm going to square root that answer. So technically, when I multiply first, I'm going to get 12, and when I square root that, I'm going to get 3.46. Now I'm rounding to the second decimal point. Technically, that decimal point goes forever and ever and ever. If we need further or more digits, we would just add them in from our calculator. But for now, I'm just going to write that as 3.46. Now, regular rounding, which we also refer to as standard rounding, uses 0.5 as a boundary between rounding up and down. So 3.47 would technically round down to 3 with regular rounding because 0.47 is less than 0.50. But with geometric mean rounding, we use the geometric mean, which is calculated as 3.46, as the boundary instead of using 0.5. So we actually say to ourselves 3.47, is it higher or lower than 3.46? It's higher than the geometric mean. Say then the geometric mean. So because it's higher, you round up. It's above the geometric mean, so you round up to 4. So this standard quota of 3.47 with standard rounding with Webster's method would round to 3, whereas with geometric mean rounding and HillHuntington's method, it would round up to 4. So a slight difference in terms of how things would round. It turns out this rounding only makes a difference when you're really close to that 0.5 mark, if you're just underneath 0.5. Otherwise, standard rounding and geometric rounding for low decimal values or high decimal values are going to work the same way. It's really when you're really close to the 0.5 boundary that things get a little sticky and things can change if you're a little lower with geometric mean rounding.